Good morning, everybody. So I guess we have an exam next Friday, and the logistics of the exam will be similar to the one we had a couple of weeks ago. I published a study guide showing pretty much exactly what you're supposed to know and be able to do. I put the study guide on the course website. And also, you want to look at that. And so today I want to finish up with the exam material, try to anyway, where we're talking about the amino acids. And then we will maybe on Monday get into a new family of reactions, and then return to amino acids in our what will probably be our final unit for the semester, talking about the proteins. I'm concerned about, one of the things that I guess I hardly ever ask you to memorize a whole lot of chemical data. Like, I'm not asking you to memorize the structure the amino acids. I'm not asking you, I've never asked you to memorize the pKa of anything. I do ask you to memorize a couple of things, but stuff that you can just look up. I don't think I'm really big into memorizing. The cost of that, the price of not having to memorize that stuff, is that you need to know how to work with the information that is given. So I want to start today's lecture by recapping a lot of the stuff that we said last time about the structure of the amino acids, but I want to make sure that you understand how to use the table of amino acids and that will accompany the exam. And remember, the exam is closed book. Right? So you're not allowed to look anything up on the internet, and you're not allowed to ask your friends or join discussion forums or anything like that. So you do need to know how to work with the information that is given. Okay, so let's make sure that we understand how to use that table, make sure that we understand how to draw the structure of an amino acid when we don't have to memorize it. Okay, so let's draw the structure of L-phenylalanine at pH 7.4. Well, this would be a very fair test question. Let's make sure that we know how to do it. Okay, so let's see. Let's go to our table. Go to our table. Okay, so there's amino acid pKa values and side chain identities. All right, so I'm looking for PHE. There it is, phenylalanine. I'm looking for PHE. And this is telling me that the carboxylic acid functionality has a pK of 1.83. So the carboxylic acid proton has a pK of 1.83. And then this table is also telling me that the alpha ammonium has a pK of 9.13. All right, so that's 9.13. Another thing that this table is telling me is the side chain. And so the side chain for phenylalanine is benzene CH2. And I don't know, I see like a little I see a line there. That does not mean a charge. That is a bond. So at the alpha carbon of the alpha amino acid, I have a benzene and a CH2. See this little line here? That is just on this table how they represent a bond. That means this CH2 is bonded to the alpha carbon. So did you get all that for this entry for phenylalanine? Okay, so I'm going to translate that information on that table. And so that is what this table, that's what that table is telling me. Okay, I want L-phenylalanine. What does that mean? So we talked about last time how the alpha carbon, that's this guy right here, the alpha carbon, for all the amino acids has the S absolute configuration when it belongs to the L stereochemical family. This is the kind of amino acid that is coded for by DNA. This is the kind of amino acid that you find in protein. So there's the alpha carbon. I need to draw the S absolute configuration there. The only exception to this would be L-cysteine, LCYS, has the R absolute configuration there. Okay, but this is going to be S. So I need to draw the S absolute configuration. So that would mean a wedge, a hydrogen here on a wedge. And I'm going to maybe dash, no, that looks ugly. I'm going to maybe dash this nitrogen like that. Is that the S absolute configuration? 1, 2, 3, reverse. Yep. So that's the S absolute configuration with the dashing and wedge. It's kind of an ugly picture, but that's okay. And then I'm supposed to draw what this amino acid looks like at physiological pH 7.4. And so that's going to mean that at pH 1.83, most above pH 1.83, most of these protons have fallen off. So that's O minus there. And this proton doesn't start falling off until we reach 9.13. So we're at 7.4. It hasn't fallen off yet. And so that would be the structure of L-phenylalanine at pH 7.4. So did you get all of that? How to use that table and how to implement and where to find these PKs. All right, so let's return to that table. I want to point some things out to you. Let's go back. Okay. All right, so first thing is that if you look at tryptophan, see this guy right here, tryptophan, his abbreviation is TRP, but it's not the first 3 letters of the name, right? TRP, the abbreviation is in bold. And if you look at isoleucine, the abbreviation is ILE. It's not the first 3 letters, but they're bolded here. Okay, so that's something to watch out for. Another thing to watch out for is that some amino acids have more than 2 ionizable groups. They all have an acidic carboxylic acid proton, and they all have an acidic ammonium, but some have more than 2 acidic protons. And so this is what they're calling here the PK of the side chain. And what I've done here is I've added little arrows indicating which proton is being removed. So if we look at arginine, arginine has 3 pKa's, one for the carboxylic acid, one for the ammonium ion, and one for this proton with the arrow pointing to it in the side chain. pKa of that is 12.48. And remember, we're only losing one proton at a time. So this arrow is pointing to NH2 plus. You don't lose both of them. You just lose one of them, right? And so a lot of these amino acids have more than 2 ionizable groups. And I'm indicating with this arrow which one is going to be removed. All right, so let's look at 2 situations. Cysteine, right? That's the one that has, oh, look how nice I am down here. All alpha amino acids have the S absolute configuration except cysteine, which is R. See, I don't ask you to memorize anything or hardly anything. If you look at cysteine, you see that the proton on the sulfur atom has a pK of 8.33. Drop down on this table and look at serine. Cysteine is CH2SH. Serine is CH2OH. The only difference between cysteine and serine is that cysteine has an S where serine has an O. But notice that the serine, that cysteine has a arrow pointing to it, but serine doesn't. And that's because this proton is, its pKa is 17, and when we talk about pH, we only go up to 14, right? So not all of these guys have 3 pKa's. Okay, so before we leave this slide, before we leave this, I want to ask you this question. Draw the structure of cysteine, CYS. Draw the structure of L-cysteine at pH 10. Draw L-cysteine at pH 10. Okay, so you're busily working on that, I hope. I'm just transcribing all of this information over here on my piece of paper on the blackboard. Be with you in a second. Okay, so I wrote down all that info from that table. So I put the side chain on the alpha carbon, right? There's the alpha carbon. That table said the side chain was CH2SH, there it is. And I just transcribed all of the pK values. And I want pH 10 so that most of these protons are gone when I go above pH 1.71. So that proton is gone. It's a negative at pH 10. This guy falls off above, most of them are gone above pH 8.33. So I'm going to 10. So that's a negatively charged sulfur atom like that. And this guy, he doesn't, most of them don't start to fall off until we're above pH 10.78. So that at pH 10, the dominant form of cysteine has all of these protons are still there. Okay, so that would be so they're taking care of the the acid-base properties. Now the L-cysteine. There's the alpha carbon. That's a chirality center. This is S for all of the L amino acids except for cysteine, which has the R absolute configuration there. So I want to be able to draw the R absolute configuration. So that's going to be what? Dash, dash, dash. 1, 2, 3. Oh, that was easy. Yeah, there's the R absolute. 1, 2, 3. Oops. That was not easy. 1, 2, because that wins. 1, 2, 3. Reverse R. And just maybe, how about maybe dashing this one? 1, 2, 3, reverse R. Yep. Okay, and so that would be L-cysteine at pH 10. Okay, and now another thing I might ask you to do, or 100% guaranteed to ask you to do on the test, how about drawing this as a Fisher projection? Remember, the east-west bonds are reaching out to hug you. So if I imagine myself standing here, there are my glasses, there's my nose, there are my glasses, there's my face, and I see how that bond and this bond, they're reaching out to hug me. I'm here, right? There's my head, right? There are my glasses, there's my head. These bonds are reaching out to hug me. And so if I want to look at this as a Fisher projection, here's my thought bubble. What am I seeing? I'm seeing nitrogen on one side, CH2S minus on the other side. They're reaching out to hug me. I see hydrogen up here, and I see CO2 minus down there. So that's L-cysteine written both as using dashing and wedging, and also as a Fisher projection. So I would like for you to please familiarize yourself with that table. Make sure that you understand how to put together the amino acids and how to work with those pKa values. Okay, so that was a review of a lot of the stuff that we said last time. So now let's continue what we were talking about, more about the acid-base properties of the amino acids. And we were talking about the isoelectric pH, also called the isoelectric point. Symbol for the isoelectric point is Pi. And this is the pH at which the sample is neutral, no charge. And when we're talking about an amino acid, this is the pH of minimum water solubility. So water is very good at dissolving stuff that has charge, but it's not that great at dissolving stuff that is neutral. So the amino acid at its isoelectric pH, at its isoelectric point, is going to demonstrate the minimum solubility. Okay. And last time I drew you a picture showing that we have dominant forms, but dominant does not mean exclusive. And we saw a bell-shaped curve and all of that. Okay, so just refer to that. What I want to talk about now is how to calculate the isoelectric pH from that table of pKa's. isoelectric point is equal to the average of the pK leading, need a lot more real estate. Good, but the PI, that is the average of the pK leading to the neutral form and the pK leading away from the neutral form. So the isoelectric pH is the pH is the average of these two numbers. Okay, so let's show a simple example and then something a little bit more complicated. Okay, for alanine at a low pH, so for alanine, right, this is alanine. From that table, I see that this is 9.69. This is a CH3 group here. From that table, this is 2.34. So that's what I'm getting from that table. This is the +1 form, right? And this is what we would have at low pH. Okay, and so now as we raise the pH, the most acidic proton, this guy, falls off. And so as we raise the pH, the dominant form of alanine becomes this guy. That's the neutral form, right? Because we have positive canceling negative overall 0. And as we keep raising the pH, that least acidic proton, that 9.69 proton falls off. And so if we raise the pH even more, we get this. This is the anionic form, right? This is the cationic form +1. This is the neutral form. That's this. And this is the anionic form -1. So for alanine, the isoelectric pH, the pH of minimum water solubility is the pK that leads to the neutral form. From here to here, I use the pK of 2.34 and the pK that leads away from the neutral form to the -1 form. That's this one. pK 9.6. So what you're averaging are the two p. When you lay out the dissociation equilibrium this way, the isoelectric pH are the numbers that surround the neutral form. It's the average of this guy and the average of this guy. Find the neutral form, the isoelectric pH are the numbers that surround this neutral form, that lead to it and lead away from it. So for alanine, the isoelectric pH is 2.34 plus 9.69 divided by 2. I'm finding the average, and the isoelectric pH is a pH of 6.02. So that's the pH at which alanine will have minimum solubility in water. And what's your pH? Anyone remember? You're 7.4. So that so that the alanine is not really that soluble inside your body because your pH 7.4 is close to the isoelectric pH of alanine. And we'll see that for most amino acids, this is true. And that's why you're not a puddle of water, because you're made out of amino acids, you're made out of proteins, proteins are made out of amino acids. Your pH is close to the isoelectric pH of most amino acids, so that even though you're 85% water, you're essentially a solid because your pH is close to the isoelectric pH of the proteins that make up your body. Anyone here ever drink like a protein shake? Or maybe you use protein powder, right? I do for a snack. You know what? That stuff doesn't dissolve very well in water. Why? Because it's made out of proteins, and proteins are made out of amino acids. And the pH of pure water is about 7. The isoelectric point of most of the amino acids is close to 7. Amino acids and proteins are just not soluble in neutral water. The pH of milk, anyone ever dissolve protein powder in milk and make a protein shake? Oh, that stuff doesn't dissolve very well because the pH of milk is 6.5. That's even closer to the isoelectric point. So, this has earth-shaking consequences, right? This is why you are not a puddle. Okay, so that was easy. That was entry level, right? Because many amino acids have 2 pKa's, most of them do. And so finding the isoelectric pH is just going to be averaging those two numbers. What if the alpha amino acid has more than 2 pKa's? Then what? It's the very same thing. You find the neutral form, and you're averaging the two numbers that surround the neutral form. So let's do that with cysteine. Let's calculate the isoelectric pH of cysteine. All right, so from that table, so cysteine looks like that, and from this table says 1.71. Table says, where are you? 8.33 for that guy. And table says 10.78 for this one. Okay, just a second here. Okay, so again, it's going to be the very same procedure. Is that we begin at the low pH and then raise the pH. We're looking to find the neutral form. Okay, so at low pH, all of the protons are going to be on. That's the +1. Okay, take away a proton. You take away the most acidic proton first. That's the carboxylic acid proton. That's the neutral. Now take away the next most acidic proton. -1. Okay, and so the isoelectric pH of cysteine is going to be, what was the pK I used here? That was the 1.71. What was the pK I used here? That's the 8.33. The isoelectric point is going to be the average of these two numbers. So let's see, 1.71. I'm just plugging these into my calculator here, 8.33. Oh, come on. I'm getting 5.02. For the isoelectric pH. So this cysteine, see, this isoelectric point is farther from physiological pH. So cysteine is, this is the minimum solubility at physiological pH. This is going to be a lot more soluble in a physiological system than alanine was. Alanine's pH is PI is a whole point higher. Okay, so this is how we calculate the PI of alpha amino acid, the isoelectric point. Is that you find the neutral form, and it's the two numbers that bracket the neutral form, the +1 to 0, and the number for the 0 to the -1. Right? And it's not always the two lowest numbers either. It's not always the two numbers that are closer together either, right? It just worked out this way for cysteine. All right. Now let's talk about reactions of the alpha amino acids. The amino acids, since they can exhibit the reactions of a carboxylic acid because they have a carboxylic acid in them, and they can also exhibit the reactions of a primary amine because under certain conditions that the alpha amino group will be NH2 and not NH3 plus, right? So we have to keep remembering about pH. So let's just look. Let's just look at some of the reactions that an alpha amino acid would exhibit. And again, the key here is there's an NH2 group in there. There's also a carboxylic acid group in there. They can, both of those types of reactivity can happen. I'm talking about reaction. I'm talking about lab reactions. RXN means reactions. Lab reactions of amino acids. Oh, we've seen this guy several times before, right? Where we had this 3 carbonyls, but we talked about how the carbonyl group is electron withdrawing, and how this carbonyl here that's sandwiched in between the two, this is the most reactive carbonyl in this molecule. And here's an alpha amino acid. Right? And notice I stripped off the carboxylic acid proton. I stripped off the amino proton. So the amino acid doesn't look like this all the time. It only is going to look like this above pH 10. So here, So this is going to be pH is greater than 10 because because the ammonium proton for most amino acids, look at that table, it's around 10. So this is a reaction that can only happen above pH 10. And what is this the recipe for? Imine formation, right? You have an aldehyde or a ketone and a primary amine. These are going to get together to form a imine. So what I'm trying to show here is that the alpha amino acid, because it has both an amino group and a carboxylic acid group, can exhibit both kinds of reactivity. Okay, so this is what we're going to get. And you know what? I'm looking at this, and I see double, single bond to hydrogen. And so what could this thing do? Tautomerize. Right, so this was imine formation. And now this thing can tautomerize, where the double bond and the single bond change places. Right, the double bond and the single bond have changed places. And what I see here is, oh, that's a new imine. That's an imine, that's an imine, but the double bond has been isomerized. And I know that imine formation is reversible. So that if I add water to this, I'm going to get hydrolysis of the imine. And this can happen under both acidic conditions or basic conditions. So what I'm going to do is I'm going to add water, but I'm also going to add water. And so that imine falls apart. And I get this guy here. Right, so that's a bunch of reactions that we have talked about before, right? Imine formation, tautomerization, and then reversion of the imine. So because the amino acid has that imine functionality, it can do all of this stuff, just like any other primary amine. Okay. More lab reactions. So those were a bunch of reactions where the amino group of the alpha amino acid was in play. Now let's look at some reactions where the carboxylic acid group is in play. And so now what would we be talking about? Acyl substitution, mostly, right? So if we have an alpha amino acid, I want OH here, not O minus, so that this reaction can only happen when I'm at a low pH. The pK of this proton is somewhere in the 2s for most amino acids, so I have to be under acidic conditions. I can't do this reaction at pH 7 because this it wouldn't be OH anymore. It would be O minus, and that's carboxylate. Look at that reactivity ladder. That's way down here. So that plus an alcohol, I'm going to call that R prime OH. I need acidic conditions, once again, so that this is OH, right? And this can be NH3+. I'm not caring about this right now. And so this is acyl substitution. There's a carbonyl-carbon bonded to something that's not carbon, not hydrogen. This is going to break off. The nucleophile is going to take its place minus a proton. So this is just a straight up acyl substitution. And remember, I'm going from a carboxylic acid to an ester, and they are at about the same level of reactivity. So I'm not really going up the ladder, or I'm not really going down the ladder. So this is an acyl substitution reaction. It's something that amino acids can do because under acidic conditions, because they are acyl derivatives. Okay, now, but something like this instead of acidic conditions, let's try basic conditions, right? Where we're not going to have ROH, we're going to have R prime O minus. What's going to happen here? Acyl substitution? Not at all, because that's a powerful base. Look at that pKa table, 17. This is a carboxylic acid. This is an acid. You don't get acyl substitution here. You're going to get an acid-base reaction. So I think we've talked about this before, is just because it has the ingredients of an acyl substitution does not mean that an acyl substitution is going to happen. And this is a problem that we see a lot of the times with carboxylic acids. pKa of a carboxylic acid is 5. The pKa of an alcohol is 17. The equilibrium constant here is 10 to the 12. That's a gigantic equilibrium constant, right? So that the acyl substitution is going to be completely defeated here. All right, so we can have esterification under acidic conditions, but not under basic conditions. Okay, so let's look at some more acyl substitution setups. So if we have, right, there's our amino acid at low pH. And now let's raise the pH so that this proton goes away. For most, so this is pH, this would be pH for most amino acids less than 2. This would be pH between 2 and maybe about 9. For most amino acids look like this. And then above 9, right, this is just that dominant form jazz we talked about so much already. That's pH above 9. So let's look at the feasibility of this reaction. Is this, I'm going to write a reaction here. I want you to tell me if it's possible, right? So is that possible? I mean, the blackboard didn't catch fire or anything, right? I wrote it here. Is this going to be possible? Not at all, because this guy, that's an amine. He's not, if this amine is positively charged, this one must be as well. So that this reaction is a total fantasy because the if this amine is positively charged, so must this one be, right? So nope, this is not going to be possible. But I'm mentioning this to say something else. What is possible is that if I were to take this guy and convert him to an alcohol under acidic conditions, that makes an ester. Now I can react this ester with a secondary, with a primary amine or any kind of amine. And now this is going to be acyl substitution. I'm going from an ester to an amine, and I can do this at really any pH I want. I could do this at neutral pH or at acidic pH. I'm going to try to do it at basic pH. At a pH greater than 9 or 10. And at this pH, this proton is going to be gone, and there isn't going to be any positive charge here either. So at above pH of 9, this becomes NH2, and this stays NH2. And so now this is going to work. So I guess what I'm saying is that you can convert a carboxylic acid. You can convert this carboxylic acid to an amide, but you can't do it in one step. You have to take the carboxylic acid, convert it to an ester, and then be careful about the pH, and then you can create the amide from the carboxylic acid, but not in one step. Okay, so as is our tradition, we can draw a heavy double line here to represent the end of the material for exam number 4. On Monday, we'll start a new unit about a new family of reactions. Any questions about anything before we sign off? Any questions about anything before we sign off? Okay, see you next time.